Hello, this is the video walkthrough for the second AI assignment, which is Road Warrior. Here we have implemented four search algorithms, which are breadth first search, depth first search, uniform coarse search, and A-star search. All these four algorithms have been implemented by using the best first search algorithms with different cost functions or evaluation functions. So we have a lot of functions and classes, mostly abstract classes here, which form the backbone of our code, but they are not part of the main search algorithm. So I'm just going to directly jump into the search algorithms first. So I have a input file, which is a file which has different nodes. It's different nodes and their path cost from one node to other, the coordinates for the nodes, and all these are in a file in the given file. So first I'm going to convert that file into a map or a graph by using this function. So I split the file into different lines and extracted the information like the different nodes and the coordinates by using just line split simple Python functions. And after I extracted all the information from that file, I created a map by using this undirected graph. So this undirected graph creates a graph which is this class. So it just takes the vertices and the path costs, and so it creates nodes. It connects the different nodes if it has the edges between them. And since we are using an undirected graph in the search, it just connects it both ways. So first we create the graph from the file. Then the next part of the execution. Here, so I've taken a start node and an end node. I've created a graph of the map of the file of this file. Let's look at it. So this is the visual representation of that of the nodes in the file, of the graph in that file. So this these are all the nodes we have, and I've selected V as the start node and AB as the ending node, that is a goal node. So our aim is to find path from V to AB by using the four different search algorithms. Where was it? So this next statement, graph problem, declares that that is our aim. That is, we are going to find a path from the start node to the end node using this map. This is also a class which has mostly just generic functions like initialization. Actions just gives us the different actions we can make from a node. That is, like, we can go to these different neighbors. Path cost gives us a path cost. Next we have, so I use this print search to just print the four search algorithms in the same standard format. So first we are going for BFS. I call this four times using for the different search functions. For BFS, I'm going to call the best first graph search by using this cost function. For DFS, again, I call the same function but with a different cost function. And for UCS, the same best first graph search function, but again a different cost function. And for A-star, again the same. So what are these and how do they work? Let us look at this function. So the best first graph search function. Here we have first create a priority queue. This is a minimum priority queue, which means the whatever node has the minimum value will be given the first priority. So for breadth first search, we have a cost function that was equal to the depth. So for breadth first search, we have a cost function equal to the depth. So initially we have just the root node in our priority queue. Then we expand the node that, and by expansion I mean we add the neighbors of the node, or in this case children. So we add U, we add W, and we add AD. All of these have a depth of 1, so they have the same priority, which is 1. Then we add the children of these nodes. So for U we had H, K, C, J, for W we had A, for L, again for AD also has L. So all these child of child nodes have a depth of 2. So since it's a minimum priority queue, the depth of the 2 is higher than 1, so they have a lower priority. So all the first level nodes will get explored first, then the second level nodes will get explored next, then the children of those nodes which have a depth of 3 will get explored, and so on until we find the final goal node. Breadth first search is more useful when we can expect that the node is closer to the root node, because we check the whole level at once. Next we have depth first search, in which we give the cost function as the negative of the depth. So actually these functions here are just simple functions that I wrote because instead of doing the arithmetic at that place, I cannot do the arithmetic at the function call. So I just wrote simple functions that would give me directly what I want. If I give the depth function, I'll just get the depth. If I call negative depth, I'll get the negative of the depth. If I call path cost, it'll give me the path cost. And for raster function, I need the sum of the path cost and the heuristic function. So this function will give me that. So I should have explained that before, but yeah. Where was I? Yeah, for depth first search, we have the cost function of negative depth, which will just give me -1 for this level, -2 for the next, -3 for the third level, and so on. So again, we have a minimum priority queue here. So this one has a priority of -1. The next level has a priority of -2, and the next one has a priority of -3, and so on. So suppose I choose the branch through U first. Then the children of U, that is H, K, C, and J, will have a depth of -2, and which means they have a higher priority than the other branches. So since these have a priority of -2, this has a lower priority and will not get executed first. So if I first go to U, then I'll go to one of these children, and then I'll go to the children of that node, and so on. So suppose we're searching for W and we chose U first, and we're going through the children of U. Then we might have to traverse a long way before we actually reach W, even if it was really close to V. Depth first search does not guarantee that being close to the root will give you the result quickly. It's more of chance. If your goal node is in the first branch, then you have a higher chance of getting it first. So next we have uniform cost search, and in here our cost function is the path cost, that is these values 185, 399, 599, and so on. So again we have a minimum priority queue here. So the node which has the minimum path cost will get selected first. In this case, it is U. So U will get selected first, and then we will add the children of U and see which has the lowest path cost. And suppose this one combined path cost that is 185 plus 64 is the lowest, then that will get selected next. Suppose some other node is lowest, then that will get selected, and then the children of that will get added to the queue, and their path costs will be compared. Whichever is the lowest will get selected till we reach the goal node. Another important part of UCS is relaxation. Suppose we have a node that is a child of two different nodes. Say we have J here. It is a child of U. It is also a child of C. So when you're first doing taking in the child nodes of U, we put in J with a path cost of 185 plus 178. But then we find it is also a child of C, and through this path we will find the path cost is 185 plus 164 plus 64 plus 54. And this path cost is going to be smaller because 64 plus 54 is less than 178. So when we find this new path, we decide to take this new path into as the actual path and discard the previous one. So we take the f of child, that is the cost function, that is the path cost, and compare it with the value in the priority queue that is already stored. And if the new path cost is smaller, then we change the priority of the child to the new one. We just delete the old child and add in a new one with the new priority value. Then we in A star we take into account both the path cost and the straight line distance from the node to the goal. So suppose we are at W, then we take into account the cost, this 399, and also the distance from W to AB. Similarly, we had to take the 185 this path cost and the distance from U to AB. So if the sum of this path cost and this distance is higher than this one, then this will get selected instead. Our cost function here is the sum of the path cost and the straight line distance from the node to here. So whichever node has the lowest value for that will get selected first here. And by this method we will not stray very far from the straight line path. So from V to AB will mostly be along like this. I don't have the exact path yet, but it'll mostly be along the straight line. It won't go away here because the straight line distance will not be optimal there. So these are the 4 search algorithms demonstrated in this assignment. Thank you.